Okay, so I think we're all here. So you can proceed, Billy. Thank you.
Okay. Today I want to get our hands dirty a bit more. We're going to be moving on to completeness next week. But for now, I thought we should actually achieve something, prove some things, and prove some things about proofs. So, so yeah, I want to actually do some cases of the soundness theorem. But before we do that, I just want to refresh your memory on what natural deduction proofs are, um, and just say some more about it. So uh, I'm making a definition here again, not on what a proof figure is, but what it means for a proof figure to be a proof from a set of formulas to some formula. So let me write this down.
Oh yeah, I'll put myself on mute.
I'm not speaking, I'm just writing. I'm writing on the first board. And I'm just in Discord, I'm not in spatial voice. Okay, so yeah, proof figure pi is a proof from, I'm defining what it means to be a proof from a set of formulas, gamma to phi. If the bottom formula is phi and all the undischarged assumptions are present in gamma, um, and write, uh, we write this. I'm not sure. It's hard to say how you're supposed to pronounce this because uh, maybe just gamma proves phi, I think is sufficient. If such a proof exists. Um, okay, so I just want to depict this just to conjure an image in your mind. So you should see, first of all, the formula phi at the bottom, and then above it should be some kind of tree developing, and you should see the assumptions as the leaves of the tree. So I'll just draw in a couple here, and they branch off due to the uh, binary deduction rules.
Billy, don't we normally read gamma v dash phi as gamma entails phi, and then the other one is gamma models phi? Or is that not like universally the terminology that people tend to use?
I have heard, I've used entails for the double turnstile for like
Oh, really?
modeling. Um, and actually, the important difference here is that when you say models, the left side of the turnstile is an interpretation there. It's not a set of formulas.
Right, so
Um,
models doesn't really make sense. I always called this entailment. That's what Johnstone defines it as. So that's tedious that there's not a distinction between the two of them. I guess we should at
yeah.
least make a decision for what we'll use.
Mm. All right, I'll make a decision after this.
Yeah.
Um, after this lecture. So yeah, so let's say we've got we have all these assumptions, but you'll see that some of them are discharged. And in this example, I'm going to claim that this counts as a proof figure for the argument for gamma equals, I could do A, C, E. So I at least need these premises. I need these assumptions in my set gamma. But I am permitted to have more things. So I can have F and G and whatever else. And so, yeah, we would probably write this, a claim like this as just, instead of without the set notation, just A, comma, C, comma, E, comma, F, comma, G, I guess entails phi. Or, yeah. Yeah, so probably a point that I think came up, but I didn't recognize it last time was you might view that there's a difficulty in looking at a natural deduction proof. This is the wrong way to look at it, I guess, to sort of a natural deduction proof doesn't tell you what the assumptions are, like what it is a proof from. Like to have a proof of something involves a decision of I'm going to produce a proof figure from this set of assumptions to this conclusion. And so then if you prefer, you might say that a proof figure is actually a pair where one is this actual figure and the other thing is the set of premises or something. Yeah, but for this, we're just going to we just have this statement that says when such a proof figure is a proof from gamma to phi. Does that make sense? Any questions about that? Okay, so
I really got the distinction. So you're saying that, for example, you could have a proof figure that had some like extra undischarged assumptions, and it might be a proof figure, but it's not a proof figure from maybe the set of assumptions that you had in mind to the conclusion. Is that right?
So it would be wrong to call it, to say it has extra undischarged assumptions, because the extra stuff we're saying is present in the set of formulas that we're saying phi can be deduced from. So in this example, F and G do not appear in the assumptions, in the undischarged assumptions of this tree, of this proof figure. Nevertheless, this piece of data, this proof figure, is a witness to the claim that that phi is provable from A, C, E, F, G.
Okay.
I've got a question, Billy. So that feels a little disjoint between what you said and what you've written. So are we going to say that a proof figure is a pair? It's a pair consisting of such a graph-like structure along with a set of hypotheses?
Well, the way I'm writing it is to not do that. I'm just saying I'm placing a condition on when a proof figure can be considered to
proof from gamma.
Yeah, from gamma to phi.
Right.
So this
Yeah.
proof figure is a proof from ACE to phi, but it's also a proof from ACEFG to phi.
Okay.
I can also add B in here, by the way. So B has the same sort of extra role here as F and G. Like, as witnessed by this proof, I am able to prove phi without B and D because I've discharged them. So I don't rely on their on them as assumptions in order to get to phi. But yeah, I can still throw them into gamma if I so please. So you should think about gamma as like sometimes if you're just doing logic like this you might never need to have more assumptions than you need for the particular proof you're doing at a time. But what we're going to these gammas are essentially going to be like our entire theory. So it's almost always going to have irrelevant stuff. That like I think it actually always will have formulas which we don't make use of, because like the set of formulas will be the set of consequences of some axioms, and there'll be infinitely many of them. Okay, so I just want to do some example proofs now. Let's go. Actually, let's stay on this board for a second. We haven't looked at negation yet, so I'm going to prove a theorem here. And there's multiple ways you can sort of state these. So I'm essentially trying to state one of De Morgan's laws in natural deduction, and I'm going to say it like this: if A or B is in gamma, then gamma proves not A or not B. Yeah, I'll go into the different ways I could have said that before, but let me continue this. So I'm going to do this bottom up. I sort of tend to favor writing a natural deduction proof from the bottom up. So let's just change to brown. So I'm aiming to get to... Oh, whoops. Someone should have pulled me up on this. This is incorrect.
I was waiting to see if it was indeed incorrect.
That would be a nail in the coffin. Okay, so yeah, so we want to get to not A and not B. A great guess is to get there using conjunction introduction, because the main connective is a conjunction. So I'm going to aim to prove not A and not B. Sorry, I've just got this loud humming in my room. I don't know where it came from. My like whole desk is vibrating.
Is it the bell from
think it's
the
the bell.
world that we're in?
I rang the bell, sorry.
It doesn't shake my desk, but
You must have some good
I
speakers.
I do have some good speakers. Actually, I think it was just from the iPad. Crazy. Okay. Please don't do that. Okay, so we haven't done negation introduction yet. But you'll find if you look at these two tablets and compare implication with negation, you'll find that not A behaves exactly the same as A implies falsum, where the falsum formula is just the always false formula. What I just said isn't true when you throw in this this classical rule, the proof by contradiction. But up until then, yeah, in intuitionistic logic, it's interchangeable with A implies false. And so the way we get to not A is by deducing it from... we're going to deduce a contradiction by including A in our collection of hypotheses. So this is going to be negation introduction. And like, I don't know, you can write A off to the side to sort of remind yourself, all right, I can use A somewhere in this proof. And so at this point, I look around and I see, all right, well, the other assumption I'm allowed to use is not A or B. And let me just erase this line. The way I just have to think about what's contradictory between A and not A or B. And so the way I get a contradiction, well, you could look at all of the rules, find one that has a contradiction below the line, and the only one you'll find is this negation elimination rule, and at the bottom right here. And so I'm going to use not A or B as my first premise to it. So I'll write that here, not A or B. And the other side, I also need to show A or B. And then by negation elimination, I will get false from that. Okay, and how? Any suggestions of a rule that I could use to get A or B from my premises that I have available?
Is it Disjunction Introduction with an A above it?
Yeah. So one of the disjunction introduction rules, and there's two of them because you can either introduce the first disjunct or the second. Yeah, the first one gets A or B from A. And so this is, if you look at this proof here, this is a proof of contradiction or of falsum from the premises A and not A or B. And so what we're going to do is blame that contradiction on A by discharging it. And then we just mark it with an index. So I'll say index number 1, and then I indicate on the negation introduction rule that I discharged that assumption. And that gets me not A. So I assume A, I perform some reasoning, I get to a contradiction, that tells me not A. Then the other side is pretty much the same. So
Sorry, Billy, do you have a choice there? Could you have discharged not A or B? That would make your theorem false, but when
if you discharge
a proof,
yeah. If you discharge not A or B, then below the negation introduction line, you would have not A or B. So if I was going from top down, I could probably make a choice there, but writing not A below the negation introduction line sort of locked me into that decision. But given contradictory premises, you can blame the contradiction on any premise and discharge it and claim not that formula. But if you're trying to prove a specific theorem, then you're going to need to discharge specific assumptions. Okay, are there any questions about this proof while I write up the other part of it? This second one I discharge with a different index.
Makes sense.
Okay. So this counts. This is a witness to the statement that not A and not B is provable from gamma, because I've depicted a proof figure in which the undischarged assumptions, which is just the formula not A or B, they are all present in the set gamma by assumption. I could have also stated this theorem a couple other ways. Let me write those here. So I could have proven not A or B proves not A and not B. And when I write this, when I write a formula on the left side, like I just mean the singleton set containing that formula. But clearly this is just a special case of this theorem. And writing the theorem in this way that sort of generalizes the set of premises allows me to not have to justify the extra step that, like, all right, because not A and not B is provable from not A or B, then if I have any larger set, then it's also provable from that. I guess that idea and what we were talking about in the definition above is the weakening rule, which is completely implicit in when I sort of talk about the undischarged assumptions all being present in gamma, because if they're present in gamma, then they're present in any larger set than gamma that contains gamma. Another way I could have stated this is that if gamma proves not A or B, so if gamma proves not A or B, then gamma proves not A and not B. And what would be slightly different here is this proof alone sort of isn't an immediate witness to that claim. What I would need to do is, above these assumptions of not A or B, I would need to sort of extract whatever proof I have of not A or B from gamma, and then essentially paste it in there. So, in all the positions that I've used that premise of not A or B, and so that's sort of treating this theorem as a sort of claim about how you can paste proofs together and sort of continue the deduction all the way to not A and not B. These things will coincide when you do something like considering a set of all the consequences of some axioms. And by consequences, I just mean the things provable from that set. And then in that circumstance, being provable from the set is the same thing as being in the set. And then these sort of different statements of the theorem coincide. Okay, any questions about that? All right. On my personal board here, I'm going to, let me put this over here. I'm going to just write up a couple example things you might want to prove. Yeah, so we have the other, I believe we did the other version of the distribution theorem for conjunction and disjunction. I'll write the other one here. So if you're in the mood to construct some proofs, you could prove this. This one, I guess, is a challenge. From any set gamma, you can prove A or not A. And you'll have to make use of the conjunction, sorry, the proof by contradiction rule there. There is, yeah, there's one more I want to prove. I actually want to do this one, which is if not exists f of x is in gamma, then gamma proves for all x not f of x. I could have stated this one with like any formula in place of f of x that like may or may not contain a free instance of x, but it simplifies the discussion if we just consider just a one place predicate f applied to the variable x. And so this is sort of new. I haven't talked about these quantifier rules, but I'm just going to write up the proof of this. So we start with, we want to get to for all x not f of x. And the way we will deduce that is from the universal introduction rule. And the way we introduce a universal statement is by proving the statement, the inner statement about some sort of abstract entity that we don't assume anything else about. So the principle that we're using there is if you just introduce some name for something, but don't specify any of the properties about that thing, like on no assumptions, you should be able to deduce the property about it. That's the sort of idea of universal quantification we're giving here. And to repeat something I said last week, it's not enough to prove the statement about all of the named things that you have, because you can have models where not every object has a name, or is even named by some term. Okay, so we're going to deduce for all x not f of x from not f of a. And so a is just a constant, a name. You could consider it an extra formal symbol as part of the sort of natural deduction system. But the rule as is displayed on this first stone here is, well, I wrote it jokingly as thou shalt not use for all introduction if a is present in the assumptions on which a with x replaced with a depends. I'm sort of glossing over the rules of substituting, of substitution and free variables. And I guess that might be a bad thing, but I'm just not going to go into that for now. But you should just think of it as a as some statement that might be talking about x, and a with a substituted for x is just that statement being made about a. So in this case, the statement is not f of x. So I need to prove not f of a, and I need to not assume anything about a. And so the way I'm going to get not f of a is from negation introduction. And the sort of paradoxical thing about this is that now I'm actually going to assume f of a. And this is now part of my set of assumptions, and it will be an assumption I use in this proof near the in the top half, but it will be discharged before I get to the universal introduction rule. So the usage of that rule will be valid. Okay. And so the contradiction, I'm going to, well, of course, I need to reach a contradiction by negation elimination. In other cases, you might use the proof by contradiction rule.
Like another hidden place where the management of the hypotheses is actually pretty scary. So you say that you don't want to say free, so you have to say something like A is discharged like all occurrences of A in the hypotheses in the branch above this for all rule are discharged at some point? Is that catch of
Yeah, well,
free?
what you do is you settle the notion of the formulas which some formula occurrence depends on, which are the undischarged assumptions used above it. So we can already, I'm claiming we can already recognize those. And amongst those, A should not appear anywhere. Okay, so I'm claiming we can get to a contradiction by using the negation.
Sorry for another question, but what's the relevant notion of sort of alpha equivalence here then? Because asking for A to not appear anywhere is kind of unnecessarily strict. If something's discharged, then its identity is sort of irrelevant, right? But you don't want to, I mean, is it just you don't want to get into that, or that is not in the sources you've looked at how they want to talk about natural deduction? Because that's kind of problematic if it's completely avoided.
So A is not a variable. It's not the same as these other variables. So there is no alpha equivalence that applies to A, because that would be an alpha equivalence that would apply to constants. So it's the constant A. Okay, so I need to get to exists x f of x in order to contradict not exist x f of x. And I've got my assumption available, f of a, and this actually perfectly matches up with the existential introduction rule, which says that if you prove capital A about any term in place of x, then you can conclude that there exists an x such that A, where A is about x. And so that's exactly what I'm doing in the top inference of this proof. I infer exists x f of x from f of A. And so here, right here, this subproof is proving a contradiction from not exists f of x and f of A. And so therefore it's from the assumption of just not exists x f of x, I can conclude not f of A, and that's the negation introduction rule. So I'll mark that there. And that therefore makes this subproof here is a proof of not f of A from just the assumption not exists x f of x. So the undischarged assumptions are just not exists x f of x, and so therefore I am allowed to conclude for all x not f of x. And so this shows not exists f of x. Sorry, not exists x f of x proves for all x not f of x. I'm going to add a similar proof that you can perform in a similar way to my personal board over here, which is not exists x f of x and not g of x. From this, if that's in your set of assumptions, then gamma proves for all x f of x implies g of x. And so clearly this is sort of you could imagine using this proof here that I've already done, where this is just an instance of pushing negation through the quantifier. But furthermore, if you then push the negation over the f of x and not g of x, then if you've done some logic before, you know that's logically equivalent to f of x implies g of x. And so you could sort of fit that sub-reasoning, that sort of lemma that converts not f of x and not g of x into f of x implies g of x. Yeah, you could fit that into this proof. It would essentially, I'm not sure, it would either fit up here in the top section or after the negation introduction. But yeah, there are multiple ways to do that proof. There's another way to do it that I sort of challenge you to find. That's sort of not the same, and I'm not sure if there's some sort of straightforward equivalence or way to transform from one to the other. But have a go at finding that. I'll write up some more practice natural deduction proofs that you can do after. But for now, I'm going to move on to actually now proving the soundness theorem. But are there any questions about these proofs before I move on to that?
Yeah, Billy, I had one question. So, what's the difference between the negation introduction rule and the contradiction rule? Is the crucial point the fact that these two rules are not equivalent to each other because we don't have that not A is equivalent to A?
Yeah, plainly it's false that like not A and A are the same formula. They're obviously different formulas. So adding this contradiction rule sort of allows it to be classical logic, and therefore you can derive that rule that from not on A you can get A. But you could also remove this rule and add that rule. Or you could even add the second, the sort of the cases rule, as in that A or not A is provable from like anything at all. And yeah, these are all interderivable rules in the context of the rest of the rules.
So can we derive the law of excluded middle from... Oh, I guess you already put that up earlier. Yeah, that makes sense.
Yeah, the law of, as in, do you count
just...
A or not A as the law of excluded middle?
Yeah.
Yeah, okay. Yeah, well,
Right, so this is classical logic. I thought this was intuitionistic.
Yeah, it's all intuitionistic until you add this contradiction rule.
Yeah, I see. Okay, cool. Thanks.
Yeah, and classical reasoning, like, yeah, it's not as natural as the rest of natural deduction. When you're like using natural deduction for classical reasoning, it doesn't. It definitely doesn't model how anyone else would think about it, because unless you sort of, I guess if you use this rule, the excluded middle rule, and just say that anywhere you can just deduce A or not A for any formula A from no premises, so like a rule that has no premises above it and A or not A below it. Yeah, and then I guess sort of reasoning by case, that's sort of the reasoning by cases in the case where A is true, in the case where not A is true. I guess that works well. I guess these other rules, like the proof by contradiction and even the double negation elimination rule, you sort of do a lot of repeated reasoning and it's a bit ugly. But I don't know, fun exercise to derive these proofs.
Sure.
Okay, let me just move on for now to the soundness theorem. Okay, and yeah, so here, this is soundness, And the statement is just gamma is any set of formulas and phi is any formula. So it's if gamma proves phi, then gamma entails phi. Yeah, I'm going to stick with that terminology. So single turnstile is proves and double turnstile is entails. Yeah, okay. So what this is saying is if there is a proof figure, which is a proof or derivation, is a proof from gamma to phi, then just a reminder of what this statement says. It says that every model of gamma is also a model of phi. But I'm going to just introduce an alternative way of saying this that doesn't involve this sort of big quantification over all models. It's somewhat more natural to actually define what it means for the crossed out version of entails. So a gamma doesn't entail phi if actually no, before I define that, I need to define what it means for given an interpretation I, what does it mean for I to not be a model of phi? And this means or first glance it just means like it makes phi false. But because truth is universal quantification over valuations, which sort of tell you what the free variables, what objects they pick out, this ends up being there is a valuation. I'm going to call it V because I'm allergic to nu. My brain can't see it and pronounce nu. So yeah, there's a valuation V such that the interpretation with valuation V of phi is 0. So that's just what it means for the interpretation with the valuation makes phi false. So phi is false with respect to the interpretation and valuation. And then to say that gamma doesn't entail phi means there is an interpretation I such that I makes all of the formulas in gamma true, and I is not a model of phi. So the role of this sort of phrasing it with the negations here is saying that the point of models is to provide counterexamples to arguments, whereas proofs provide witnesses to arguments. So as in the proofs provide witnesses to arguments that are actually sound arguments, and models are for showing that some argument is not a sound argument by providing a counterexample in which all of the premises are true and the conclusion is false. So let me begin the proof here. We proceed by induction on the number of inference rules in the derivation or in the proof figure. Maybe I'll just say inferences instead. So I mean the individual inferences used. So what I mean is, so this, like, it's not really sensible to say the proof figure, I guess, because the premise, we're saying if gamma proves phi, then gamma entails phi. The if gamma proves phi, that's, I don't have a proof figure there, and there could be multiple such proof figures. So to clarify, I'm actually proving this statement, which I'll parameterize by n. So the statement P of n is if there is a derivation of phi from gamma with at most n inferences, then gamma entails phi. And so we're seeking to prove this statement for all n. And so the base case is pretty easy. And so this is the case where we have 0 inference rules, and there is such a proof here. So there is one proof of phi with no inference rules, and that is the proof which just has phi as the sole undischarged assumption and phi as the conclusion. So if I were to draw it, it's literally, I just draw phi, and that counts as, that is the proof from phi to phi. So if there is a derivation of phi from gamma with at most 0 inferences, well, then I have if there is a proof of phi from gamma with 0 inferences, then phi is actually in the set gamma, because there's only one such possible proof. And so then it's plain to see that then gamma entails phi, because this is a statement that that if you have an interpretation that makes all of the formulas in gamma true, then it also makes phi true. And phi is in gamma, so that's tautologically true. So that's the base case. I'll move on to the next cases here. Okay, so here's my inductive case. So I don't have to write again. I'm going to say just suppose P of n. So I'm supposing that if there's a proof of phi from gamma with all the proofs of phi from gamma with the most n inferences, if I have one of those, I can deduce that that gamma entails phi. And so now I get to my inductive case. So now suppose there is a proof we'll call it pi of phi from gamma with, suppose I have to say at most because that's the nature of my statement, with at most n plus 1 inferences. And this is where I need to, we have to proceed by cases on the last inference rule. So that's the inference used to get the conclusion of the proof. So now, suppose it is implication introduction. This is the case I'm going to do. I might do 2 cases actually. And so then it then pi, the proof, has the form. So we have some assumptions from gamma, some discharged collection of assumptions from, or assumptions of A. We get to B, and then there's a usage of the implication introduction rule that discharges that collection of statements, that collection of assumptions of A. And when I write this is just common notation to say, like, I'm just denoting a proof of, like, this whole proof is pi, and above the line is a proof of B from gamma and A. So now I have to argue that then the proof figure obtained by removing the final inference. So I mean removing the line, the label, and the formula below the line. And replacing any occurrences of a discharged assumption of A labeled by I with an undischarged assumption of A. That thing is a proof of B from gamma union with the formula A, and it's with at most n inferences, because I just removed one and I started with at most n plus 1. So then by my inductive hypothesis P of n, we have gamma union A entails B. Okay. So what do we need to prove now? We need to prove that gamma entails A implies B. That gamma entails A implies B. So I'm going to proceed by contradiction. And so this is where I'm using my definition from the board just before, that that gamma doesn't entail, well, it's not the case that gamma entails phi if there's an interpretation I which makes all the formulas in gamma true and makes phi false. So proceeding by contradiction, I'm going to say, suppose I is an interpretation such that I makes gamma true and I makes A implies B false. Yeah, and then unpacking I makes A implies B false. I know therefore there is some valuation V such that I with that valuation of A implies B is 0. And the reason I need to dig down to this depth of the semantics and involve the valuation is just this is simply where we have defined when a formula with a main connective of implication is made equal to 0 by the interpretation and valuation. So this is where like this concept is defined. So it's 0 exactly when so now we have I of V of A must be equal to 1 and I of V of B must be equal to 0. And that's by the semantics. And we also have I of V of whatever formula psi is equal to 1 for every psi in gamma. Yeah, I'll continue on the next board. This tells me that well the second thing I said tells me, and I makes all of gamma union A true because I started with the assumption that it makes all of gamma true, and I've shown it also makes A true. I am a little unsure about it making. So it should make. I'm claiming that this is true. That A is true in the interpretation, but I just started with the fact that the interpretation with valuation V of A is equal to 1. Clearly, the valuation isn't super important here, but that seems like an important detail. I would have to revisit that where that comes into the argument, but so I'll just admit that to be unjustified, but claim that nevertheless it is true that I makes gamma union A true. What I have shown, the other thing I have is that I does not make B true. And this is specifically witnessed by my interpretation and valuation, which makes B equal to 0. So I'm confident of that part at least. But this here serves as this contradicts. Try that again. This contradicts the assumption that gamma union A entails B. And so the assumption I started with was that there was an interpretation that made all of gamma true and made A implies B false. So therefore I can, so there is no such I, so therefore I can claim that gamma entails A implies B. And that proves the statement P of n plus 1 in the case where the last inference rule is a implication introduction. Any questions about that just yet? I'm at my 12 o'clock. I could go a bit longer if Will thinks you won't take up the whole hour. Will, I think you're on mute.
Yeah, sorry, just noticed that. Yeah, I'm more than happy to let Billy keep going. I'm not going to take a full hour, but I did have a question as well. I got a little bit confused by that part that you got, that hurdle. This seems like a complete proof to me. Is there a hole in it at the moment?
Okay, so this statement gamma entails A is that this says for any interpretation I'm not talking about gamma here. I'm just talking about I. The statement that I models A, that says for every valuation V, I with V of A is equal to 1.
Yeah.
But I think I've only shown that I with V of A is 1 for this particular V.
Yeah, so I of V of
Somewhere,
A is equal to 1 for a particular valuation, but I of V of B is not equal to 0 for this particular valuation. And so that's a contradiction.
it is equal to 0. I of V of B is 0.
Yeah. And so that's a contradiction that for all valuations, gamma union A entails B. So isn't that complete?
To contradict gamma union A entails B, I need gamma union A, all the formulas in that set to be true in the interpretation for any valuation.
Oh, I see.
I think somewhere there is a stronger hypothesis in this proof that I've extracted a weaker statement from. But I guess this gets to all right, the usage of valuations has sort of tripped me up here. But one thing to notice is that all of these proofs of soundness will, for all the different cases of the rules, will boil down to proving some appropriate statement about entailment. And for this one, it's just if gamma union A entails B, then gamma entails A implies B. And so if you believe this, then you believe that the rule is sound. Yeah, and the same is true for the other one. So sort of the act of performing the soundness rule is just proving a bunch of relationships between different entailments. And I can write down a couple examples. So for the conjunction introduction rule, I'm going to need to prove that if gamma entails A and gamma entails B, then gamma entails A and B. And the reason why I'll need to prove this is because in my proof that starts with the premises in gamma, or at least some of them, and then ends with a conjunction introduction rule. From this, I will gain two hypotheses. I will be able to infer that gamma proves A and gamma proves B with a proof figure with at most n inference rules, and then I can apply the induction hypotheses to both of those to get gamma proves A, gamma proves, not proves, entails A and entails B. And then my job is to just from those hypotheses get to gamma proves A and B. And so from that point, it's just verifying that the semantics agree with this. Yeah, so that's the two parts of this soundness proof, is figuring out how the structure of the tree corresponds to which entailment sort of lemma I need to prove, and then like verifying or at least believing that those lemmas, just recognizing that the semantics validates those. I'm going to continue and do a more interesting rule. So let's do pose the proof figure as the form the proof from gamma to capital A with A substituted for x, to for all x A of x. That's a universal introduction. And I'm just as a reminder, well, if this is a valid proof figure, then we have where A does not appear in any undischarged assumption. I'm foreseeing a hiccup that will, it's not really a hiccup, it'll just become a sort of lemma to prove. But I hope you'll believe it. So then the proof figure actually, I guess from this point, I'm just doing the same thing where I'm like extracting the subproof and claiming that it's a proof from gamma to A with A substituted for x. But the sort of statement that I'm going to need to prove is the following. Oops. If gamma entails A with A substituted for x, then gamma entails for all x A. Yeah. And actually, I'm going to say like a sort of extra hypothesis to this lemma I'm proving. Where should I write this? Is an extra condition. If A is not present in any formula in gamma, then if gamma entails A with A for X, then gamma entails for all X A. And you so the issue I was sort of recognizing here is that I've is that this proof figure here, it might not have any lowercase a's in the undischarged assumptions, but as a proof from gamma, like gamma might have a appear in some of the formulas in the set gamma. So, but I can get out of this by recognizing that, all right, this subproof counts as not only a subproof from gamma, but it also counts as a subproof of just the set of undischarged assumptions. So, what I don't apply the inductive hypothesis like to having a proof from gamma to capital A with A for X. I'm applying it to the subproof, which is a proof of the argument from just the undischarged assumptions to capital A with A for X. Is it clear the point I'm making?
I feel like I understand it.
Okay, cool. So yeah, it suffices to just prove this case where if A is not present in any formula in gamma. Okay. Let's see. So suppose or contradiction. Yeah, I think I'm going to run into the same issue, and I'm going to fix it now with by modifying the statement. This is equivalently if it's not the case that gamma entails for all X A, then it's not the case that gamma entails A with A for X. So now I can still just work with one interpretation and one valuation. There's something I'm doing wrong in the other proof that requires me to do more than that. So yeah, this is just the contrapositive statement. Okay, so the hypothesis that if gamma doesn't prove or doesn't entail for all X A, that gives me, then there is an interpretation I with I also have a valuation. Valuation V such that I makes all of gamma true and I with V of A. Hang on. I'm going to introduce the evaluation after this. Yeah, with I makes all of gamma true, and I makes for all x a false. So then there is an evaluation. V with IV of for all x a equals 0. And this sort of then gives me, or by the semantics rules, or the definitions, this gives me a V prime. So there is some V prime with I V prime of A equals 0. So this is just saying, if for all x A is false in this interpretation, then A is false for some valuation V prime, where V prime is just sending x to some particular object of which A is not true. So it's the witness object that A is not true of. Okay, so now we
Billy, does this
find
valuation V prime restrict to the valuation V on all other variables other than X?
Yeah, I need to say
Do you
that.
need that?
Whoops, it's too big. Yeah, I probably will. Let me say it like this. There is some this is either done with talking about variance of evaluation or just like picking an object and modifying the valuation with that object. I'll just go with the latter. So there's some object D in the domain of the interpretation, such that now V subscript x prime, V subscript x maps to D is the same valuation, except it maps the variable x to the object D. And x maps to D of A is false. So there's some object D for which if you send x to that object, then A is false in the interpretation. So now here's the trick. We define a new interpretation. I prime, which is identical to I, except the name it gives to A, the object that A names is now different. So the object that I prime assigns to the name A is now D. Yeah. So then I claim that then I prime with valuation V of A with A substituted for X. This also has to be false, because this essentially compiles to the same thing. Here I'm switching to the interpretation I prime, in which A now names that object D, and so this would be proved by just an induction proof on the complexity of the formula, which is just recursively identifying that that you'll get the same truth value out of this in these two different ways. So the first way is the valuation, when it gets to the variable, will send it to the object D. But in the second way, we're replacing the variable x with a name A, and in our interpretation I prime, A names that same object, so we're going to get the same truth value. So now this gives me, so I prime is not a model of A with A for x. But we do have, I prime, we claim, is a model of all of the formulas in gamma, since A does not appear in gamma. And so this is like the important part of the proof. This is that the principle of excluding A from appearing in any undischarged assumptions. This is just justifying that if you modify an interpretation so that the name A refers to something different, then it doesn't have any effect on whether that modified interpretation makes some set of formulas true if A doesn't ever appear in that set of formulas. Okay, so these two facts, that I prime makes gamma true, and it also makes A with A for x false. Those two facts are contradictory to gamma entails A with A for x.
Billy, I'm a little bit confused with the way that you've written this. Like, didn't we say earlier that the important part was A may appear in gamma, but we just don't apply it to the entirety of gamma. We just apply it to the subset of it where A does not appear within it.
Right here, I'm proving this lemma here, and then
okay.
And so I prove that. Yeah, and then I extend that to, I just apply that to the inductive argument on the structure of the formula by saying this applies because I'm not actually, the gamma I'm going to apply it to is not the same gamma as appears here.
Yeah, got it.
Yeah.
Thanks.
Yeah, so that's a taste of the soundness proof with involved with the quantified rules, and I showed you one before with a propositional connective for implication. But yeah, the other rules are sort of the same exercise, and yeah, you can sort of list out all of the different relevant entailment proofs that you would need to make use of in your inductive argument. And so that's the soundness proof. It's just verifying that these rules and the sort of corresponding entailment relations that they correspond to, they make valid inferences about the semantics. And so I'll wrap up my main time there. But is there any questions before we move on to the next part?
Yeah, I just have a query. I guess at some level I don't really buy soundness. Isn't it the case that what you're actually doing here is there's an informal proof system that you're using to reason about the model when you say things like IV of A equals 1 or 0. You mean
Yeah.
there's some kind of argument there, but you don't want to say what the proof system that the argument takes place in is. But essentially what you're doing is proving, I mean, you're taking the proof of phi from gamma and reconstructing it in this informal proof system, which is what the thing you're writing on the board is. Is that a valid way of reading what you're doing?
I never started with a proof of phi from gamma that wasn't a formal thing. So I'm just starting with these formal etchings on the page, and I am associating truths about the arrangement of those symbols with entailments in my semantics. Like I've never thought soundness isn't like, you could think of it not as a theorem, and like it's literally just a sanity check. It's the lowest possible bar for a proof system. It just, if it wasn't sound, then you would write a different proof system. So like you do actually start with these entailment relations, and then you go, all right, let me come up with some rules
but
that reflect them.
I mean, do you start with the entailment relations? I mean, I guess the emotional valence I'm supposed to associate to this is something, seems like, okay, I believe in models for some reason, and I believe in this reasoning about interpretations, and then it's a sanity check on the formal logical system. But isn't it actually kind of the reverse? Isn't it more like, okay, over there's this informal reasoning system, and it can't be too crazy, because when I actually write down what I really mean by proving A implies B, it does line up with what I was doing over there.
What is the thing you were doing over there? What's the informal reasoning thing?
Well, when you say, so there is some object D in ID, such that blah, blah, blah. I mean, if I dig into what it means for IV of a formula to be equal to 0, there's some statement. If I dig into what it means for IV of A or B to be true, there's some statement. Right? And that statement is, what is that statement in?
I've always been like rather unsatisfied with the sort of semantic side. Like I could sort of always make sense of the proof side, like these formal structures. This all makes sense to me. I always feel uncomfortable writing the object D on the page, because it's like, I don't know, there's a sense in which like I know that not everything can be named, but now somehow I'm like the thing I'm naming here could be some like undefinable real number or something, that has no like term that like picks out exactly that real number.
Yeah. So I just want to check if we're on the same page conceptually. So the way I think about this is that this is a kind of check that I am indeed formalizing the logic I think I'm using.
Yeah. So the like main way this is conceptualized is that there is a meta theory, and this proof system is and it's like first order language is the object theory. And so I never say formulas. Like you never there's no point in any of these proofs in which you say like, well, if for all xa, then blah blah blah, because that's sort of I'm then saying the formula for all xa. But because I'm the meta theory and it's the object theory, I must always be saying something about the formula, because I'm thinking of it as a sequence of formal symbols, and it's not itself a statement. And then like that kind of leads to kind of I don't know, stupid ideas like, let's just have like infinite tower of meta theories in which each meta theory is like rests upon, which is I think is absurd and not satisfying at all. And so yeah, I've always been somewhat uncomfortable with the semantic side and what it even means to like this. I mean, we'll see this in when Will defines the rules of the semantics. It's all the rules just sound like stuttering. Like A and B is true if A is true and B is true. Like you're not ever explaining what these connectives mean. Like you have to already know what they mean.
Yeah. Okay, good. I guess unless there's another important question, we should probably move on to Will so we have time for that. You still think you have time to fit it in, Will?